Boys and girls, I'm recording this for the second time now because the first one was kind of laggy. Things started going in a wrong direction, so I'm going to talk about what is time complexity in today's video. So, first of all, the definition of time complexity. Basically, it's a standard way of analyzing and comparing different algorithms. So I'm kind of sick. So if my voice is, I'm going to of course increase the voice volume later. But uh, for now, I mean it. I'm sick, just so you know. So when we are talking about time complexity, you need to know what is n notation. But first of all, let's see what does the letter N represent. N stands for amount of data. Amount of data. Like this video if you know that already. So I make this video more interactive. So the second things. Oh, by the way, N can be. It's usually integer, not usually, but all the time. It can be, let's say, we can work with 100 pieces of data or 1000 or whatever number. It can be any number basically. So what is annotation? Let me draw. In order to explain this concept, I need to draw you a picture, somewhat of a picture. And I want to use different colors. So here we have, or let me just draw this box which represents a program, and from in every program you have, let's choose that again, and here the fans kicking in. So welcome fans to the video. So we have input that goes inside a program. You can imagine this program being sort of like a function, and we have input as parameters. Let's say this is parameter n that goes inside our program or function, and then the function gives us an output. And this is basically the scheme for every program out there. And basically what we are comparing here, what is annotation, how we compare algorithm is we take this input, it's, as I said before, some number n, and we want to know how much, not depending, but basically the output is a function of n again. So compared to this, how much times how much units of there's some unit of time here, and I want to type in n, or let's type in with a different color. Let's type in m. Here we get a number, or not a number, not as a result, but we get an n. And so this n number I wrote is just a function of n, but in n notation you just type in n. And we want to know, given the input n, how much, let's see in the notes actually, given the input n, the number of data, what is going to be our output in some sort of unit of time. So if we have, let's see a more practical example, so because it seems like I cannot explain this concept. If we have 10, let's say 10 units of something, 10 users, let's say, in our program, or 10, I want to use this example of a supermarket. Let's say we have a supermarket. This is the program for supermarket, and we have only 100 products, and we're looking for one product. And if our program, let me just uh, let's start a new drawing because it will be very clear now. This is the program again. This is the input, and here we have an output. Let's say we have n products, and this can be 100, let's say, in a supermarket. And if we give that to a program, then, and let's say the units of time that this program takes to figure out or to find this this one product we are looking for is 100 seconds, or it can be any unit of time, minutes. So we don't worry about the unit for now. And the thing is, we want to make our, let's see if I have written that here. We want to make our program that scales with input size. So if this is gets, let's say, our business or our supermarket gets somewhat bigger, and we get 1,000 products, we don't want this 100 to become something like 1 million. We don't want, so this, you can represent this data in somewhat of a graph or whatever this is called. If this here on this y-axis, if we have, let's say, what do we have here? Here we have the number of inputs, number of data, and here we have, I'll probably should change colors and I chose the same color. So if we have an output here, we don't want something like this. And basically, here's the output. If the input increases just a bit, and the output, the time it takes for the program to finish the output is so big, you don't want that. You want a program that scales. And that's basically how you compare algorithms. And this is all actually. I need to write once again. This is a function of n, so it could be n, the same, or it can be n squared, or it can be, now I know why it's undo the, it can be n on the third, n cube, I think it's what's called, etc. And now for the second part, let's see if you can hear me. Yes, you can. So, I'm just going to help you refresh your knowledge on what is a logarithmic function. So, you need to know logarithmic function because we want to remember this thing where, of course, you do. This is the input, and this is a function of the output, and is basically the function. We want to make somewhat of a logarithmic function here because that way, as input grows this way, and the time it takes is kind of sort of less and less. This is a logarithmic function, and that's why I'm going to give you a refresher on what is a logarithmic function. So I just want to get a different color, and now let's see, check the notes. So the logarithmic function is the inverse of exponential function. Boom, red color there. And exponential function goes like this. I very much like exponential function. We want our business or whatever you have, or you as a person, to grow exponentially, but usually, and by the way, skip this part. I just added it in because usually, if you're growing, let's say your business growing exponentially, and you just gotta at some point uh, hit this curve, hit this plateau, and after that start going even down less and less. So the since the logarithmic function is the inverse of exponential function, since it's not like this, then it's sort of like this, as I've mentioned before. So how you define, not define, but I don't know the word, but how you define a logarithmic function is like this. You say log base 2, this stands for base, and a number, it's a 64, and I should wrote this number as well. So let's just start here, and choose this color for log, and then another for the base, and then another for our number. So, and let's say this is x. Let's undo it times, then get x. So, uh, this what it means is just ask you 2 on which exponent I think it's called is 64. And let's first of all actually take 36, or probably not. And let's see how much is that. 2 times 2 is 4. This is 4. This is 16. And then we need another 2, which will make 32. And then we need another 2 to make 64. So this is 1, 2, 3, 4, 5, 6. So x is equal to 6. This is a logarithmic function, and the point I'm trying to make here is, let me just take another example of a logarithmic function. Remember this thing, or so you don't have to remember. I'll just write here logarithmic function of base 2 to 4 equals to 6. And here's another one. Logarithmic function base 2 with 128 is equal to, guess what, 7, because 2 on 7 is 100, etc. I mean, you can go on and say, logarithmic function with base 2 with number. What's the next number? Let's just add those two. And by the way, I love writing on this tablet. And that's why I'm just even writing this makes it's satisfying. So this is the next number. I completely forgot. 256. You don't want to see. And if you make choose a different one, log base 2 from 256, then we have this is 7, so this is 8. If you just time this you make this times 2, you will get this number, and this is 7. I mean, this is 8. So that's a logarithmic function. As you can see, these numbers, imagine this being the input. Finally, I came to my conclusion. Imagine this oops, this being the input, the n. You see how this grows sort of exponentially. If you have a y and a z axis, if you have let's say here we have 64, then 128, and then 256. This grows like this exponentially. We have this, and this, and on the x-axis we have 6, 7, and 8. So it basically doesn't grow like at all. So I wrote this sort of wrong, but it doesn't really matter. So that's why you need to know logarithmic functions. The second part, or mistakes were made. The third part is actually there is a, let's say, it's called 2.5 part, where I'll be talking about. I want to mention that in a program, let's say you have some code. This is the first line, second, third. What you need to do is just count the steps. So here, if this line of code let's choose, this line gets executed n number of times, and n is the number of data. You kind of type that in. If it's 2 times n, you type in 2 times n, and you basically just count the number of times this line executes. This, let's say, executes 4 times, etc. And this executes, let's say, 2 times. So if we sum up these numbers, we get 2n plus 6, and this is our complexity. And now we come to the annotation scaling rules. And to calculate, you just need to count the steps, and we don't care about multiples. We take the largest in an equation. So this is the example I gave to you, but it can be somewhat like this, just so it makes more sense to you. 3n squared plus n plus, let's say, 9. The numbers doesn't really matter that much, all that much. And let's take the red one, like a teacher. So we don't care about multiples, so scrap this. And we don't care about these numbers. And we are left with this n. So how does this program scales? And I want to make it box, just so you can kind of refer to the previous thing when I made a program with an input and an output. So this is how our program scales, and it's not really good in most cases, because if you have 1000 users or units of data, this is n, the input, and you put it in your program, then you get an output, and your output is again 1000 because it's n. And let's say in this example, how you count the steps. This is the first step, and then you need to determine the complexity, or how your algorithm scales. You don't care about multiples, scrap that, and you don't care about adding the addition of this number. And you take, remember the third one, you take the largest in an equation, and this means basically just the largest this here and this one, but you don't want one, you want the largest exponent. You scrap this end, and you're left with n squared. So this is basically the complexity of this algorithm, and this is probably the worst algorithm you can get. So be aware and be scared if you see n squared. You should be scared, because if you have 100 users, you get n squared, and that is n squared time, that is 100 squared, which is 1 with 4 zeros, and that is 2000, I mean 10,000, sorry. And that's a lot of time, even if it's in second, minutes, or whatever. Imagine if you have, and you probably have more than 100 to be honest, most cases you have 1000, then in squared would be 1 million. And this is how much you want in your bank account and not in your program. So the next thing is, actually I want to talk, take rest and then talk about the next thing. So if you're still watching up until this part, you're probably a big fan. I don't know about fan, but you probably have something, you have something you like about this video, so make sure to subscribe. And we've come to the big O notation, and you may wonder, why is it so big, Code Nerd? I mean, why is it called big notation? Because see how big it is? This is why it's called big O notation. So just kidding. You'll see in a bit why it's called big O notation. Actually, I don't know why it's big, but you know. So programs, I want to mention here, the programs don't run at exact time all the time. Sometimes they run slower and sometimes faster. And let's just make new, and then without losing my train of thought, let's say you have somewhat of a client-server architecture, and this is a long line. This is a one long line. And we want to make this somewhat bigger. Hopefully you like my simple drawing. This is a client and this is a server. You know, sometimes the server has many what are they called, requests, many requests to handle, and sometimes it cannot sort of give you a response right away. So that's, in the server is basically slow. But sometimes when you don't have all of these requests, the server will be fast. And what we want to do is kind of what big O notation is it represents a boundary, or the worst case. What's the worst case if this server or our program or our algorithm in the servers will run out? Is it in 100 seconds? Is this the worst time that it can run? Is it 10 seconds? This is probably great, or maybe not. So basically, let's go back to the notes. Once I've deleted this table, the big O notation represents a boundary, and we have some other. And let me just, I don't know why I didn't already, but big O notation represents something like this. It's typed like this: O with parentheses, and here we write N, or I should add different color. There we go, precise. So I can add N, or depending. This is basically this part, and I'm referring back to this. This is this part. Remember the output, how much time depending on, not depending, but reflecting the data. If this is n data, depending is the same n. So is it n squared, is it only n, is it n cube, or etc. This is how you represent the big O notation. And there are some other notations, like this is, here they are, the Greek symbols. And these all represent a boundary. So this is this just represent different branch. And why do we need to use different notation? Because, well, because um, so everyone speaks the same language. Because we have, let's say here, PC1 or not, let's say PC1 with a head count in the discourse, and PC2, and now this PC may be faster than this one, so it's you cannot compare it. It's unfair to compare algorithm on this PC and this PC. If this is the slower one, or and this is the fast one, it doesn't matter. So we want to compare different algorithms based on uh, the amount of data or how the scale given and input size. So that's all I have to say with this video. Hopefully it didn't come out too long. So make sure to subscribe and see you in the next one.